Good morning, everyone. Hello. So, I'll just get the sound. Okay, you can hear me. No sound. I think. Oh. Do I have to do something here? Hello. I think the chair will use these mics, right? It's such a good. Wow. Cool. But anyway, we'll. Well, while they're sorting out the sound, if you can hear me. So, just welcome again, everyone. Thanks for being here. Good. Okay. Thanks very much. Welcome, everyone. Thanks again for being here. Just very quickly, I'm going to hand over to the chair now, but just in general, if there are any issues or anything that you would like to announce or things, send it to one of us. You'll see any of the volunteers around. How's the first day been so far? Okay, not too bad. We haven't had too many reports of bugs. There have been, a few technical glitches here and there, but I think they're ironing out all the bugs, especially in the e-poster system as well. But just bear with us. We're trying a lot of new things, but I think in general things are flowing smoothly. Just a big thing for all the speakers in any of the sessions, just bear in mind that everything is streamed and there are online participants, so think about them. And I think all the speakers would have seen that if you don't want something streamed, then you can always speak to your technician. We hope that everyone will be happy to have everything streamed. Just a reminder that all the messages, try and join Slack if you haven't already, and we can make any announcements and things on Slack. If there's anyone that has any problems at all, our team is always ready to help. So please feel free to contact us if you need anything. So with that, welcome to the first plenary. I'll hand over.
Good morning. My name is Ilya Mandel. I'm here on behalf of the SOC of the IAU 389 Symposium. So very welcome to the Gravitational Wave Astronomy plenary session. Also thanks to our SOC co-chairs, Sumaya, Nisanke, and Paul Hrud, who are sitting in front. And we have a fantastic lineup of speakers, so let's get right to it. And our first speaker is Silvia Biscoviano. Silvia, please.
Good morning, everyone. Thank you for tuning into my talk so bright and early today, and thank you to the organizers of the Gravitational Wave Symposium for the invitation. My name is Silvia Biscoviano, and I'm currently a NASA Einstein Fellow at Northwestern University, and I'm giving this talk on behalf of the LIGO-Virgo-CAGRA collaboration. So the organizers asked me to tell you about the latest results from our ongoing fourth observing run, 04. And I'm definitely going to tell you about our most recent observations. But more specifically, I'm going to tell you about the astrophysical insights that we've gained from the compact object mass distribution that we've measured with our gravitational wave observations. So let's start by taking a step back and taking a broader look at our observational landscape in gravitational wave astronomy. We are now able to probe gravitational waves across many decades in frequency. So in this plot, you can see the sensitivity of various facilities as a function of frequency. Starting all the way on the left-hand side, in the low frequency or nanohertz regime, we have pulsar timing arrays. And these represent an international effort using radio telescopes around the world to detect the gravitational waves that we think are emitted by the slow in-spiral of supermassive black hole binaries. And you'll hear much more about nanohertz gravitational waves later on in this session from Ryan Shannon's talk. But this talk is going to focus on the high frequency end of the spectrum on the right-hand side of this plot in the audio band, so in the range of tens to thousands of hertz. And we probe this regime using ground-based gravitational wave interferometers. So our current ground-based detector network consists of 5 interferometers. There are the 2 LIGO detectors in the US, the Virgo detector in Italy, the Japanese detector Kagra, and then there's a smaller detector in Germany called GEO600 that's mostly used for research and development. Construction also recently began on the LIGO India detector, which we hope will become operational towards the end of this decade. Now, so far, all the gravitational waves that we have observed with our ground-based detectors, we think come from the merger of compact object binaries that include black holes and neutron stars. So LIGO is not sensitive to mergers that include a white dwarf component. Those will instead hopefully be probable in the millihertz part of the frequency band between nanohertz and audio bands with the future space-based detector, LISA. So before we jump right into the new observations, I wanted to start with a very brief history of our gravitational wave observations to date, and I'm sure that this will be familiar to many of you. So the first direct detection of gravitational waves came in 2015 with the observation of GW 150914. And the naming scheme of gravitational wave events just encodes the date on which the event occurred. So this particular event occurred on September 14th, 2015. And it was determined to come from the merger of 2 approximately 30 solar mass black holes. Now, most fundamentally, this event taught us that black hole binary systems exist in the universe. And they can get close enough that we can observe their merger within the age of the universe within a Hubble time. So before this detection, there was no other observational evidence for the existence of stellar mass binary black hole systems. And we also didn't know if there were some binary evolution processes that could actually bring these systems close enough so that we might observe them merging. Now, a couple years later came the detection of the first binary neutron star merger, GW 170817. And this is so far our only multi-messenger observation. So in addition to the gravitational waves emitted by the system, it was accompanied by a host of counterparts across the electromagnetic spectrum, from the radio all the way up to the gamma rays. And you'll hear much more about electromagnetic counterparts to compact object mergers in Kenta Hotakizaka's talk up next. And then finally, in 2020, we completed our portfolio of compact object binaries with the detection of the first 2 neutron star black hole mergers, GW 200105 and GW 200115. Now, these 2 events occurred within just 10 days of each other towards the end of our last observing run, 03. So at the end of 03, we had accumulated 90 total significant gravitational wave detections. And this plot is just showing the cumulative number of events that we've detected as a function of observing time. Well, we are now in the middle of our 4th observing run. So during the first half of the run in 04A, we accumulated 81 new significant detections in our online observing mode. And so far, during the second half of the run, we have found an additional 37 events. And you'll notice that there is a significant increase in the detection rate in 04 compared to 03. So we're now detecting gravitational waves typically a couple times a week. And to make that more quantitative, we're able to detect binary neutron star mergers out to a distance of about 150 to 160 megaparsecs. While in 03, this binary neutron star range was only about 100 to 140 megaparsecs. So already in 04, we have more than doubled the number of gravitational wave candidate events that we have observed. And 04 will continue for about another 10 months until June of next year. Now, on a more personal note, I joined the LIGO Scientific Collaboration in 2015 in the summer for a summer undergraduate research project. And right as my summer project was wrapping up in the fall, we directly detected gravitational waves for the first time. And so I thought, this is an amazing time to be a gravitational wave astronomer, and this is what inspired me to pursue my PhD in this field. And I hope that by the end of the talk, I'm going to have convinced you that it's still an amazing time to be a gravitational wave astronomer nearly 10 years after our first direct detection. Okay, so let's take a look at the masses of these compact objects that we've detected so far in gravitational waves. Here in blue, you can see the black holes that we've detected in gravitational waves. In orange, the neutron stars, and then for comparison, in pink and yellow, the black holes and neutron stars that have been detected electromagnetically. And just for the sake of clarity, the x-axis on this figure does not carry any information. It's just the y-axis that conveys the mass of the object. And so already looking at the masses of these events individually, we can begin to distinguish some interesting features. So up towards the top of the plot, you'll notice that some of these individual black holes have masses that are consistent with or in excess of 100 solar masses. And typically, the black holes that we're detecting in gravitational waves tend to be more massive than those that have been observed electromagnetically. Now, looking down towards the bottom of the plot, you might notice that there are some mystery objects that are colored both orange and blue. And this is because, based on our gravitational wave observations, we cannot distinguish whether the object is a black hole or a neutron star. Later on in the talk, I'm going to highlight one event that contains a mystery object, GW230529. And this was actually the very first event that we detected at the start of 04. And the detection and implications of this event were recently published in APJ Letters in a paper that I co-led. So we don't just want to look at the masses of these objects individually, we also want to consider the population as a whole. And you can see here the compact object mass distribution that we infer using our latest gravitational wave observations. So these are specifically the masses of the heavier objects in the binary or the primary object. And there are two different models shown here. In blue is a more flexible data-driven model, and then for comparison in green is a parametric model that encodes some of what we know from the astrophysics theory side to assume a specific functional form for the mass distribution. So throughout the talk, I'm going to argue that this compact object mass distribution provides us with key astrophysical insights into the formation and evolution of these compact objects. So what can we learn by looking at this plot? Well, starting on the high mass end, on the right-hand side of the plot, we think that black holes with masses between about 45 and 100 solar masses should not be able to form from direct stellar collapse. And so by looking at this mass distribution, we can potentially gain clues into the formation of these most massive stellar mass black holes. Now, we think these objects shouldn't exist potentially because of a particular kind of supernova mechanism called a pair instability supernova or a pulsational pair instability supernova. And so in the massive stars with initial masses in the range between about 150 and 250 solar masses, we think that they will undergo this pair instability supernova mechanism where the whole star gets completely blown apart, leaving no remnant object behind. But when we actually look at our gravitational wave observations, we find that we actually have evidence for the existence of black holes in this upper mass gap between about 45 and 100 solar masses. So either what we think we know about pair instability supernova physics needs to be revised, or there is some other formation channel that is leading to the formation of these objects. And one possible explanation is hierarchical mergers. So these will occur in dense stellar environments like globular clusters or nuclear star clusters, where you have lots of stars and compact objects, and they're constantly dynamically interacting with each other. And in some cases, they will pair up and merge. If the remnant of that merger is retained in the cluster, it could potentially pair up and merge again. And so if that merger remnant came from two 30 solar mass black holes merging, we would infer it to have a mass of 60 solar masses, and hence it would occupy this upper mass gap. Now, what if we look instead on the lower mass end of this distribution on the right-hand side of the plot? Well, in this case, we could potentially find evidence for or against a gap between the most massive neutron stars and the least massive black holes. Now, the earliest evidence for the existence of this lower mass gap came from the observation of galactic X-ray binary systems as early as 1997. And you can see a very early version of the same compact object mass distribution based on these X-ray binary observations in the upper panel of this figure. And it wasn't until about 15 years later that a theoretical explanation for this gap was proposed, which depends on the delay timescale in the supernova that leads to the formation of the compact object between the moment of core collapse and the eventual supernova explosion. So depending on the delay timescale between these two events, you can either end up with a predicted compact object mass distribution where this gap is filled, as you can see, for example, in the yellow and green lines in the bottom panel of this figure from the paper by Balchinsky et al. From 2012, or you can end up with a mass distribution that reproduces the lower mass gap that had been observed in X-ray binaries. Well, what if we now update this mass distribution with our gravitational wave observations? So one issue is that we don't actually know where the edges of this gap should be because we don't know the maximum neutron star mass. And this is due to uncertainty in the underlying nuclear physics that governs the internal structure of neutron stars via the neutron star equation of state. But we think that this maximum neutron star mass should be at most about 3 solar masses. And so we say that this lower mass gap lies from about 3 to 5 solar masses. And if we look at this range in our gravitational wave mass distribution measurement, we can see that it's definitely not a completely empty gap, but there might be a dip or a dearth of compact objects in this mass range. So before the start of 2004, there were a few compact objects that we detected in gravitational waves with masses in or around the edges of this gap, sometimes within quite large uncertainties, as you can see, for example, from the object on the right-hand side of this graphic. But our most significant evidence for an object having a mass near this lower mass gap came from the secondary or less massive object of GW 19.14, which we measured to have a mass of about 2.6 solar masses. Now, all of this changed at the start of 2004 with the detection of GW 230529. So I already mentioned that this was the very first significant event that we detected at the beginning of 2004. And the primary or heavier object in this binary, we measured its mass to lie staunchly in this 3 to 5 solar mass gap. So this event was observed just with the LIGO-Livingston detector. The other interferometers were either offline or had insufficient sensitivity to observe the event. And even though we only saw it with one interferometer, we are confident that it is of astrophysical origin because the event was independently identified by 3 different search pipelines. So because the heavier of the 2 objects in this binary lies in this lower mass gap, there are 2 possible interpretations for this event. The first is that it's a very heavy binary neutron star merger, where both of the components in the binary have masses between around 2.3 to 2.5 solar masses. So this would be the most massive binary neutron star merger we've ever observed. The other possibility is that this event comes from the merger of a neutron star with a very low mass black hole in this lower mass gap. And in this case, this would be the least massive neutron star black hole merger we've ever observed. Now, when we fold in what we do know about nuclear physics, we find that there is an at most about 10% chance that the system was actually a binary neutron star merger. So we really think it was the merger of a neutron star with a low mass gap black hole. So not only is this event under the neutron star black hole merger interpretation, or NSBH, as I might abbreviate them throughout the rest of the talk, not only is it the lowest mass NSBH, but it is also the most equal mass neutron star black hole merger observed to date. And so you can see here the posterior probability distributions that we infer for the masses of the compact objects in this event in teal, and then for other events in a similar part of the parameter space in gray. And there are also these dotted lines, so that denote different mass ratios. The dotted line on the left corresponds to equal masses between the neutron star and the black hole, and then the dotted line on the right corresponds to a mass ratio of 1:5 between the neutron star and the black hole. So looking at the posterior for GW230529, we can notice that the primary mass overlaps exactly with this gray shaded region corresponding to this lower mass gap between 3 and 5 solar masses, and it has an extended tail of posterior support all the way out towards equal masses, and it gets much closer to that equal mass line than the other neutron star black hole mergers to the right of it on this plot. So this also has implications for the population level compact object mass distribution that we infer. And what we find is that when we include this new event in our population, this actually decreases the minimum mass of black holes, specifically paired with neutron stars, so in the neutron star black hole merger population. And you can see here in green the mass distribution that we inferred for the black holes paired with neutron stars with all of our previous neutron star black hole merger detections. And there is significant uncertainty in the minimum black hole mass, but it's somewhere around 6 solar masses. And then when we update our inference to include GW230529, you can see that the minimum black hole mass, the uncertainty decreases, and it shifts so that it's somewhere around 3 solar masses. And this has implications for the existence of this lower mass gap between neutron stars and black holes. And so when we look at the existence of this gap specifically in the NSBH population, we find that including GW230529 decreases the probability of the existence of a gap from 98.6% all the way down to 7.2%. Now, we can also look at the merger rates of events like GW230529 and the more standard unequal mass neutron star black hole mergers that we'd previously observed. So in blue here, you can see the posterior probability distribution that we infer on the merger rate for the new event. In green, the merger rate that we infer for events like all the previous neutron star black hole mergers that are more unequal mass, and then in white, the combined total NSBH merger rate. And interestingly, it seems like GW230529 is at least as common as the more vanilla unequal mass NSBH mergers. So even though this event is less massive, which means it's more difficult to detect because we have an observational selection bias where more massive objects produce louder gravitational wave signals, it seems like out in the universe, events like this one with mass gap black holes are actually just as common as the more unequal mass neutron star black hole mergers. And this has implications for the multi-messenger prospects of neutron star black hole mergers. So whether or not a particular merger will potentially be accompanied by an electromagnetic counterpart depends on the outcome of the merger, which in turn depends on the properties of the binary. So there are basically 2 possibilities. The first is that as the neutron star inspirals closer and closer to the black hole, it will plunge directly into the black hole, leaving behind no remnant material that could potentially power an electromagnetic counterpart. And this occurs preferentially for rigid neutron stars, for unequal mass ratios between the neutron star and the black hole, and for small black hole spins. The other option is that the neutron star will be tidally disrupted outside the black hole's innermost stable circular orbit, leaving behind some remnant material that forms an accretion disk around the black hole, which could potentially power an electromagnetic counterpart. And so this probability of tidal disruption is enhanced for more deformable neutron stars, for more equal mass ratios between the 2 objects, and if the black hole has a large prograde spin aligned to the orbital angular momentum. Now, we already saw that GW230529 enhances the fraction of the population of neutron star black hole mergers that we think have more equal masses. And so this in turn enhances the probability of these sources being electromagnetically bright. So the detection of this event means that NSBH mergers are more likely to be multi-messenger sources. And you can see here the posterior probability distribution that we infer on the fraction of neutron star black hole mergers that we detect in gravitational waves that may have an electromagnetic counterpart. Now, the exact number of these multi-messenger events that might be detectable will depend on the details of your favorite survey and also on some astrophysical uncertainties, like, for example, the numerical relativity fitting formula that we use in this calculation. But in this most conservative case, before the detection of GW 230529, we found that at most 6% of our NSBH sources that we were detecting in gravitational waves may be electromagnetically bright. When we include GW 230529, this upper limit increases to 18%. Okay, so to wrap up what we've learned from GW 230529, this event likely corresponds to the merger of a neutron star with a low-mass black hole whose mass lies exactly in this lower mass gap. So the existence of this object challenges compact object formation paradigms that traditionally enforce the presence of this gap between neutron stars and black holes in the mass distribution, and it specifically can teach us something about this supernova delay timescale. This event enhances the multi-messenger prospects for NSBH mergers, and it also raises questions about X-ray binary selection effects, because if we can observe low-mass gap black holes like this in gravitational waves, why aren't we also seeing these objects with our X-ray observations? So what's on the horizon for the LIGO Virgo Kagra detectors? I already mentioned that 04 is going to continue until June of 2025, and then the instruments will come offline for an extended commissioning break where upgrades will be made. And then we hope that the LIGO detectors will come back online for the 5th observing run at their A+ design sensitivity in the middle of 2027. And at this point, we expect that optimistically we'll detect binary neutron star mergers out to a distance of as far as 325 megaparsecs. So the predicted sensitivities for the Virgo and Kagra instruments are more uncertain, but we also hope that they will have similar significant improvements in sensitivity. Okay, so hopefully throughout this talk, I've convinced you that the future of gravitational wave astronomy is loud. We talked about how the compact object mass distribution that we've measured with gravitational waves provides insights into the underlying astrophysics behind these compact objects. So, for example, the supernova mechanisms leading to their formation and the formation channels that lead to the production of compact object binaries. I told you about how the information that we can gain from individual exceptional events offers us complementary insights into what we can learn from the population as a whole. So the individual events allow us to probe specific corners of the parameter space, while the whole population allows us to probe bulk features. And finally, 04 has already more than doubled the number of gravitational wave detections, and we hope to be able to tell you much more about the rest of these new observations over the coming year and beyond. Thank you, and I'm happy to take any questions.
So thanks very much again to Sylvia for a fantastic talk. Questions? Oh, Matthew has a question. Do we have a microphone for Matthew? Okay, I think somebody's running over here with a microphone, Matthew. Thank you.
Yeah, thanks for the nice talk. Can you comment on what the lack of neutron star mergers means for the ability to be able to make meaningful comments about the Hubble constant in the short term, and also at the end of 05, based on the upper limit on the rates that you must be seeing?
Yeah, so that's right. We haven't actually observed any additional neutron stars in 04, we think, so far, based on the public information. I think this places our updated neutron star merger rate on the very lower end of our previous estimates, which with 2 events were quite uncertain. And so I think the typical estimate is that you need something like 100 standard siren events before you can get a % level measurement of the Hubble constant. And so, I mean, I think it seems unlikely that we'll get there during 05, but we'll see.
Thank you.
More questions? There was a question. Matthew? Oh, sorry. Could you bring a question? Could you bring the microphone? Oh, there was someone else? Oh, sorry. Okay. All right. Well, okay. Sorry, I apologize for not seeing you. Okay, let's start here first.
Sorry. Nice talk, Sylvia. I was wondering, the X-ray binaries are not detected in the gap. Could it be a statistical issue? Maybe there are very few and, you know, it's hard to see them. Is that possible?
Yes, so I think there are two possibilities. Either it's some sort of like observational selection effect that those objects are not as bright, or it's some like astrophysical selection effect whereby those objects just don't end up existing. I think we have enough X-ray binary observations at this point that, I mean, it's possible that they exist and they're just very rare, but already the significance of that gap in X-ray binaries is, I think, much more pronounced than what we're observing in gravitational waves.
Yeah, thank you for the talk. Can you just very briefly tell us about the templates that are being used in O4, and in particular, do they incorporate things like eccentricity driven by three-body interactions from a third distant body? Thanks.
Yeah, so the templates that we use do not incorporate eccentricity effects. They also do not incorporate the effects of spin precession, so they assume that the spins are aligned to the orbital angular momentum, and they also generally don't incorporate tidal deformability effects on the neutron stars, and this is just during the search phase. So when we then do detailed source characterization, we incorporate all of these effects with the exception of eccentricity, where there is still significant work needed to be done on the waveform development side. But there have been like safety studies done to make sure that basically by ignoring these effects, we're not missing large swaths of the population.
Thanks very much again, Sylvia. I think we'll have to stop here with the questions, but I'm sure Sylvia will be happy to answer them afterwards. So thanks again. And our next speaker is Kenta Kotakazaka. Kenta, please.
Can you hear me? Yes. Thank you, Ilya. Thank you very much for being here. I'm Kenta Hotokezaka. It's my great pleasure to be here. So, there's no slide yet. Oh, yes, it's coming. So I'm going to talk about electromagnetic signatures of gravitational wave mergers, but here I mean gravitational wave mergers by two neutron star mergers. And let me begin with several key questions regarding the neutron star mergers. So one of the most interesting questions is our mergers are really the origin of heavy elements. Here I mean heavy elements by the heavier than iron. Where's iron? Iron is somewhere here. Oh wait, somewhere here. And then heavier than iron, there are two kinds of processes that responsible for making elements. One is R process, nucleosynthesis, another is S process. So I'm talking about R process elements, which we think that neutron star mergers are responsible for it. And we want to make sure that we want to measure how much mass, how much elements, and which elements are really created in neutron star mergers. So this is one question. Another question is about gamma ray burst and mergers. So traditionally, we classify gamma ray burst in long GRBs and short GRBs according to the duration of the burst. If it's longer than 2 seconds, we say it's long GRB, and shorter than 2 seconds, we call it short GRBs. And traditionally, we think that long GRBs are powered by collapse of massive stars, while the short GRBs are powered by neutron star mergers. There is some evidence, but we don't really know what's going on so far. And I will talk about kilonova, but kilonova is a electromagnetic signature of neutron star mergers. And sometimes we see some kilonova-like signature after GRBs. And we have seen, for example, several kilonova candidates after short GRBs, so which means these short GRBs actually may be neutron star mergers. But recently, we see some kilonova candidates in also long GRBs, so which means probably some of long GRBs are powered by also neutron star mergers. And of course, there are some supernovae candidates in short GRBs, which means some short GRBs are also produced by core collapse. So nowadays, this long and short classification is kind of controversial. So we want to understand this connection. And actually, there is some diversity in neutron star mergers. And I'm showing you here is a numerical relativity simulation of two neutron star mergers with the same equation of state, but slightly different masses. So the top is 2.7 solar masses in total, and the bottom is 2.9 solar masses. You will see some significant difference in the merger process. So now this lighter one merge and the heavier merge. And as you can see, if the neutron star mass is slightly heavier, it directly collapses to a black hole. While it's a little bit lighter, some massive neutrons survives. So this makes some diversity in neutron star mergers. So in summary, for example, if you have neutron star merger with different masses, say if it's very heavy, it just directly collapses to a black hole, and maybe there is a tiny disk around it. If it's very low mass, it will not collapse to a black hole, just make a supermassive neutron star, and there is also the intermediate state. So probably sometimes tiny disk may not drive jet, and some cases we will see a jet, some cases maybe not. And also kilonova signature may vary with this diversity. For example, maybe this is dark kilonova, this is maybe dim kilonova, and bright kilonova, superluminous superkilonova, so on and so forth. This is what we expect to see after the gravitational wave mergers. Okay, let me make sure everyone is on the same page. So this is what happened in 2017. So this is the first neutron star merger detected by gravitational waves. And still, this is the gravitational wave neutron star merger event that we see electromagnetic counterparts. So what happened was in August 2017, the LIGO detector saw a gravitational wave from neutron star merger, and 1.7 seconds after the burst, there was the gamma ray burst, and half a day, people discovered the optical, infrared, and the UV counterpart. We call it kilonova. I sometimes refer this event as AT 2017 GFO. This is the name of this kilonova event. And later, we saw afterglow. I will also talk about afterglow a little bit later. Okay, so this is the outline. So I will a little bit more explain about what is kilonova, and then specifically what we have learned in this specific event. And also I will a little bit talk about afterglow. And there is a new excellent observation of JWST about this GRB. I will also talk about this kilonova event. So what is kilonova? So when neutrons are merged, there is some mass ejection. Let's say after the merger, as well as like 100 milliseconds after the merger, we expect some mass ejection going on. And because this ejecta is extremely neutron rich, so we expect our process nucleosynthesis happens in this ejecta. So let me show you the animation. So this is again the merger simulation. You see some material is ejected, and the ejected velocity is about 0.1 c, 10% of the speed of light, and the ejecta mass is usually order of 1% of the solar masses. And because this ejecta is so neutron rich, I'm going to show you some animation about our process nucleosynthesis. So this is some animation. So this axis shows proton number of nuclide. So each point shows different nuclear species, the proton number and neutron number. So initially, they're here, and those nuclei capture free neutrons and goes up to the heavy elements. So something like this. And here is the stable nuclei. So they have to first initially very neutron rich so that they are very unstable and gradually decay toward stable nuclei. So actually our process decay is the source of the kilonova. So after the our process nucleosynthesis, which occurs on about time scale of 1 second, and after the our process nucleosynthesis finishes, they decay, undergo the beta decay. So this is the energy source of kilonova. So we don't see initially the light because the ejecta is still so dense that photon cannot diffuse out from the ejecta. So, but around 1 day, photon can diffuse out from the ejecta, we start to see kilonova emission. And then actually radioactive heating keeps heat up the ejecta, so we continuously see this. So this is what we see. So this is the luminosity as a function of time. So the points here show the observed light curve of the kilonova that we see in the GW7017. And blue line here is the expected R process decay. So one remarkable thing here is the observed light curve actually roughly follows the heating rate. This is actually very kind of robust prediction of R process nucleosynthesis that the heating rate shows this kind of power law. So this is, we think this is one strong evidence that actually R process occurs in neutron star major ejecta, because what we see, the light curve is following the heating rate. So from this light curve, we can estimate how much R process elements we need to explain the light curve. And from this argument, we concluded that about 5% of R process nuclei are formed in this ejecta in kilonova GW7017. And what about spectrum? So of course, astronomers want to see spectra where are atomic lines. But let me briefly, overall, this is the spectrum of this kilonova from 1.5 days to about 10 days. So overall, initially it's blue, so the temperature is above 5,000 Kelvin, let's say. And it's quickly, the temperature gets cold. Let's say around 9 days already, the temperature is about 2,000 Kelvin. This is very rapidly evolving because the expansion velocity is much faster than supernova, so that this evolution also occurs much faster than supernova. And on top of this black body-like radiation, we see some line features. Can anyone recognize any elements? It's very difficult. Actually, it took us so long to claim which one is actually look like absorption lines and what element actually causes absorption lines. But still, this work is going on. But now, let me tell you the current situation. So this is the current situation. So we think there are 4 absorption lines, at least. So yttrium-2, strontium-2, lanthanum-3, and cerium-3. And I think you can, the most remarkable line structure is here. You can see this looks like absorption lines, right? And after subtracting the continuum, you can see like this is P Cygni like absorption line and emission line. This is typical line shape of the expanding medium. So here is P Cygni of yttrium, strontium, and lanthanum, and this might be cerium. And also, okay, I should mention that we will have several talks regarding this line identification in this afternoon. So if you are interested in, please come to the symposium. And there are other feature appears at 2.1 micron later phase. This looks like emission line. So these are the absorption lines, and this look like emission line. So now I move on to the emission line features. In the early phase, still the photosphere exists. So there is above the photosphere, there's absorption lines, which makes like this kind of P Cygni line feature. But in the later phase, photosphere disappears because the density is so low that the emission just escaped. So in that phase, we call nebula phase. In nebula phase, the emissions are dominated by emission lines. So we calculated the spectra of the nebula emission of the kilonova. So we constructed a line list of the forbidden lines of R process elements, which contains about 10,000 forbidden lines of heavy elements. So this is what we expect for the neutron star major nebula phase. So the peak is actually around 2.1 micron. This is around 10 days after the merger. And this actually tellurium is the strongest line that we expect. And actually, what we see in the GW7017, the peak at later phase is about 2.1 micron. So we think this emission line-like feature is actually caused by tellurium-3 forbidden line. And tellurium-3 forbidden line is expected to be strong because this is actually one of the most abundant elements in our process. Like this is, the tellurium is sitting on exactly the second peak of our process. Okay, so let me summarize. So this is what we have identified. So there are probably strontium and yttrium and tellurium here, and lanthanum and cerium. So still we are working, people are working that line identification of other elements. So difficulty here is we don't have complete line list at near infrared where the kilonova emission peaks. So in the future, we have to make sure we have to prepare all the line list in the realistic, experimental data, and then we can ask what kind of element actually can be identified in the kilonova spectrum. Okay, this is mass budget of our process. So given the rate of the neutron star merger inferred from the LIGO observation, so we can convert this rate to the galactic event rate of neutron star merger. So this is unit of per million years. And this is mass per event. So I said it's about 5% of solar masses. So this is what we learned from the kilonova. And in order to explain all the our process elements in the Milky Way, the rate and mass ejection must be around here. And there's other experiment as well. So actually, it's now the rate and mass ejection is very consistent so that the neutron star mergers can explain all the our process element in the Milky Way. And regarding the rate, so this one actually corresponds about 1 per year within 100 megaparsec. So as we have already learned from Sylvia, that LIGO now can see neutron star merger out to 150 megaparsecs. So we will see neutron star merger maybe this year, if they are actually providing our process elements. So we will have some trouble if we don't see them. Anyway, okay. Let's move on to afterglow quickly. So this is afterglow light curve. Again, this is observed flux and as a function of time. Now this is the unit of year. So here is 0.1 year, 1 year. Now it's about 6 years or 7 years after the merger. So we are still doing observation of the afterglow. So this shows a beautiful power law, goes up and then down. And this power law nature shows this, looks like jet. So initially, we see that this jet away from the axis is slowly rising. And at the peak, we start to see the jet core and reach the peak and then power law decline. And the surprise was that the VLBI observation shows the significant motion of the jet. So this is the jet position at 75 days after the merger, and this is 240 days after the merger. Within the 150 days, the emission of the radio emission region moves significantly. So this motion actually gives you the superluminal motion with a Lorentz factor of 4, so that we are sure that what we see is relativistic jet. And also, we don't really resolve the jet, which means it's narrowly correlated. So therefore, we conclude this is relativistic jet and narrowly correlated. So this is the animation that the interpretation of the afterglow. So there is an ejector that power kilonova ejector, let's say kilonova ejector, and within the kilonova ejector, the jet is launched later. And jet propagate inside the kilonova ejector, and at some point, the jet breaks out from the ejector. And if we have seen this event from on-axis, we would have seen very powerful GRB, because the energy estimated from the afterglow is very large. But we have seen this from about 20 degrees from the axis. So what we saw was quite weak gamma emission. And it's keep expanding. So after the injection stops, still jet expands into the ISM. Now it's the scale of the sun. And it keeps expanding. Let's take some time. And at some point, we start to see the afterglow. It's still expanding. Now the size of this is about the solar system, and we start to see the afterglow. So afterglow is driven by the shock between the ISM and the jet head. And now this is the light curve that we see, and this is the motion that we see in a VLBI observation. So within the 100 days, it moves few milliarc seconds. So this is what we see as a superluminal motion. And afterglow light curve looks like this. Okay, because we have seen the superluminal motion, which is very sensitive to the viewing angle to the jet, so we can estimate the angle between the jet axis and the observed viewing line of sight. So this is the posterior distribution of the distance to the gravitational wave source and viewing angle. So this is what gravitational wave tell us, like there is some degeneracy between the distance and the viewing angle, and VLBI observation can tell you what is viewing angle. So this actually a little bit help to estimate the distance to the source, and this is the posterior in the Hubble constant. And with just gravitational wave, you can tell the Hubble constant like this. This is already very excellent. And adding more information of the jet, we can actually narrow the posterior distribution of the Hubble constant. So this is one interesting application of the jet observation. In the last 5 minutes, okay, I want to tell you the recent JWST observation of the kilonova candidate after this gamma ray burst 23037A. Okay. So this is very peculiar burst in the sense that this is extremely bright gamma ray burst. So this is the burst, how bursts look like, and duration was about 40 seconds, which is typical long GRB. It's not short GRB. And actually, this is, in the observed flux, was the second brightest ever. So this is the first brightest, and this is second brightest. And unfortunately, LIGO, Virgo, Kagura were not in operation, but this is very peculiar long GRB. It's very bright. And there are other interesting remarks. For example, so there was JWST observation, and this is the first spectroscopic observation for a kilonova candidate after GRBs, and one of the nearest GRB, and the second long GRB associated with a kilonova candidate. Okay, so this is the JWST image of this burst. So this is the most probable host galaxy, which is about 300 megaparsec from us. And this is what we see. This is the burst location. And you can see the very red point here. Actually, in the JWST image, it's already looked very red. So this is consistent. The kilonova should be red. So, and the offset is quite large, like 40 kiloparsecs, which means that this is not collapsar, because if it's collapsar, it should be somewhere in the star-forming region, but it's large offset. We think this is not collapsar. And how light curve look like? So this is the light curve. So now, because we see this on axis, there is strong afterglow. Actually, not very strong afterglow, but on top of the afterglow, we see the kilonova-like emission. This is the bump because of the kilonova. And actually, the light curve is very similar to what we see in GW1717. And actually, this is a very red object that's seen in JWST. So this is another surprise that JWST spectrum, how JWST spectrum look like. So this is the spectrum, let's say this black one is the spectrum at 30 days after the burst. And on top of that, it's overplotted is the kilonova GW1717 spectrum at 10 days. And surprisingly, the there is an emission line feature, which is the same location, about 2.1 micron, which look like tellurium emission, plus some red continuum. So the light curve and spectra are both look like kilonova, what we see in the first gravitational wave merger event. And mass that we need is also about 5% of the solar masses. But so these indicate actually this is actually kilonova and also showing some hour process signature. But because this is first GWS observations, we don't really know how the actual neutron star merger, gravitational neutron star merger look like in this longer wavelengths. So we want to see the GWS spectrum at longer wavelengths. And we are hoping that in this year we will see such event. Okay, let me summarize. So in the first neutron star merger event, we see kilonova. And estimated mass of the hour process element is about 5% of the solar masses. And in the spectrum series, we saw some P-Cygni-like features. And from this, we can now tentatively identify the strontium, yttrium, and lanthanum, and cerium. And also, in the later phase, we see some emission line at 2.1 micron, which is attributed to tellurium emission lines. And we saw afterglows with superluminal motion. And we have excellent GWST observations, and we are looking forward to seeing another event in the gravitational wave. Thank you very much, and I'm happy to take questions.
Thanks for the great talk, Kenta. Do we have questions? It was so clear that there are no hands raised. Oh, I see a hand over there. Seth, please.
Hi, thank you very much for the talk. I was wondering how many binary neutron star mergers need to have a jet to manage to get the short GRB or long GRB number, basically, observed?
How many, oh, you mean in terms of the beaming?
In terms of, like you were saying in the initial bit, you had some mergers don't get a disk and don't get a jet.
Oh, yeah, I see.
What fraction do you expect to have?
Right, that strongly depends on the mass function. I mean, how the mass of the binary neutron star merger distribution look like. So it seems like LIGO shows the merger mass distribution is kind of wide, sometimes low, sometimes massive. So I think after observing like 5 or 6, we can have some distribution because this happens very narrow range of the masses, like 2.7, 2.6, 2.8. So with this kind of distribution, we already can see probably the difference in the jet and kilonova. So identifying 5 or 6 EM counterpart would be already very interesting in this context.
Vivek has a question in front.
Thanks for the nice talk, Kenta. I was wondering, have people used the offset in this very bright long GRB with the kilonova to like place constraints on the kick velocity or the delay time between merger and formation?
Oh, yes, you can estimate the offset. We don't know the delay time. Let's take 10 billion years of delay time. Then within 10 billion years, you can bring 40 kiloparsec. I can estimate, but I can tell you later quickly. It's possible.
Sorry, I'm just, oh yes, there's a hand in the back, sorry.
Okay, thank you for the interesting talk. Maybe it is interesting to emphasize that the simple long and short distinction in the GRBs are only the first approximation. For example, the merger in the 17 was a intermediate long GRB if you are consider the soft part of the emission. So it's depending on the detector, and somebody are telling that there are 5 different classes of GRBs. So at least I think there are 3 classes, but anyway, in the classification method could be quite different, and maybe the original sources are somehow involved in that kind of processes.
Yes, thanks for the comment. I completely agree with you that probably we have to think about, reconsider about the classification and why some GRBs just last for 2 seconds, why sometimes 40 seconds in the mergers.
Okay, we have time for one remaining question. If not, let's thank Kente very much again. And last but not least, we will have Ryan Shannon telling us about pulsar timing arrays. Ryan?
Good day. Yes, I'm very excited here to be telling you a story about using an observatory the size of a galaxy to observe distant black holes. We observed this observatory with the most powerful radio telescopes in the world. It's a story decades in the making, hundreds of astronomers, tens of thousands of hours of observing time. And I'm especially excited to be here in South Africa because I want to share to you the important role Meerkat is playing in this endeavor and will continue to play over the next few years. So our detectors are radio pulsars, neutron stars beaming radio emission that we can observe with our radio telescopes on Earth. They've got metronome-like precision. This pulsar is rotating every second or so, but the detectors we use are millisecond pulsars. And we use this technique called pulsar timing. So this is arguably, in my opinion, the best pulsar. It's got a very sharp profile here. It's got a white dwarf companion. It's in a nearly circular orbit. We know that the orbit is not perfectly circular. It's 1.14 times 10 to the power of -7 eccentricity. To put this in perspective, the orbit is 570,000 kilometers in size, and the difference between the semi-major and semi-minor axis is 2.7 microns. And we know that. This is a star that's 3 times 10 to the power of 16 kilometers away. So with this pulsar, this is a pulse profile, and the signals that we're trying to see now are a factor of 10,000 to 100,000 smaller than the rotation period of the pulsar, which is 2.947 milliseconds. What we do is we observe these arrival times over the course of decades. This is the first millisecond pulsar that's ever been observed, and the power of the pulsar timing technique is that it is phase coherent. This means that signals that are very small in Doppler shift accumulate over time. This is a data set that started in 1984, and it continued into 2022. And I know that between the first observation and the last, the pulsar has rotated 585,999,381,787 times. Full stop. So with these things, with these pulsars, we can now measure these arrival times we can convert into changes in distance between the pulsar and the Earth. And for the best pulsars, we can time to precisions of tens of nanoseconds. So light travels a foot in a nanosecond, and so you can think about changes in arrival times for these pulsars, that's roughly 3 meters, for pulsars that are 3 times 10 to the power of 16 kilometers away. So to put that in perspective, for this pulsar here, if this was a gravitational wave, I could estimate the strain of this gravitational wave based on how much the arrival times have changed over the course of this time. And it's roughly a millisecond. It turns out that 40 years is roughly a billion seconds, so the strain for this would be 10 to the minus 12. However, this isn't a gravitational wave. This is the pulsar spinning irregularly. And we have to keep this in mind when we're trying to build our gravitational wave detector. Again, we're looking at a nanohertz frequency gravitational waves. Sylvia showed this plot earlier, and you can see here that we're in a very different regime, looking at very different sources than the LIGO Virgo that we heard about earlier in the previous talks. So the primary signal that we expect to see is from binary supermassive black holes. I'll go into a bit more detail about why we expect to see that in a minute, but we also have to keep in mind that there's other sources of gravitational waves in this band, potentially. And the results of the last few years have really motivated a lot of the theoretical, work in understanding what amplitude signals can be produced by these things. So we can think about cosmic strings and superstrings and signals from the early universe. The most likely source to see when we begin with is a stochastic gravitational wave background. So this is the superposition of all the gravitational waves emitted in the nanohertz band in the entire universe that we can see. However, we have to also keep in mind that there could be other sources that might dominate if we're lucky. So this includes single sources that could be evolving or non-evolving, and there's also we could also potentially see gravitational wave memory events. So in terms of the most likely astrophysical source, it's from binary supermassive black holes. So this is a story of the evolution of the universe. So we know that galaxies merge. As the galaxies merge, the nuclei of the galaxies get closer together. The supermassive black holes that we think are the centers of these galaxies are dynamically dragged together through stellar friction and potentially gas. Eventually, they become so close that their hardening, the way they're merging or coalescing, is driven by gravitational waves. And when they're at around a milliparsec separation, that's when we expect to see the gravitational wave emission in the pulsar timing band. Eventually, they get close enough together that they sort of get out of the pulsar timing band and are potentially then eventually detectable with LISA. So the key here is that these gravitational waves that we see, that we could be seeing from these binary supermassive black holes, are telling us about galaxies, right? They're telling us about, we know that supermassive black holes play a very, very important role in regulating galaxies, and they're really providing us a very unique way to study galaxy formation and evolution. So, what does this, what type of signals do we expect from these gravitational waves? So this gravitational wave background is the sum of all the gravitational waves that are being emitted, and it's what we call a stochastic signal. It's a red noise signal. This plot here is just showing an example of a hierarchical merger of binary supermassive black holes over time. As galaxies merge, the black holes merge and grow in size. The first signal that we expect to see is what I call background noise. This is a rumble in our pulsar timing data sets that has the same statistical properties in different pulsars, but is statistically independent. So there's the same sort of noise process, but statistically independent. And so this is an example of what this background noise might look like. This is a plot showing you simulated timing residuals, and this is the same statistical process, but has different realizations, so they're independent. The signal is typically characterized by an amplitude and a spectral index, and we'll be seeing plots showing this A and gamma in a few slides. But the other thing to keep in mind is that one of these sort of awfully looks a lot like what we saw from that first pulsar. So we're going to see a noise process that's similar to what potentially could be from the pulsars themselves. So that's the challenge, right? So there's other processes in our timing pulsar data sets that can look like the gravitational wave background. So what we need to see is the angular correlation. Gravitational waves are quadrupolar, and when you average over all the gravitational waves in all the directions in the sky, what you'd expect to see in the correlations between the different pulsars is what's called this Hellings and Downs correlation function. So what you see here is that pulsars that are close together in the sky have a high degree of correlation. Pulsars that are around 45 degrees separated have no correlation, and 90 degrees have negative correlation. So what we need to do is look at our data sets, look at an ensemble of pulsars, and see this correlation. So that's what we call a pulsar timing array. So these are these ensembles of millisecond pulsars observed with the most sensitive decimeter wavelength radio telescopes on the planet. These are major efforts that have been going on for decades. In Australia, we have the Parkes pulsar timing array. Europe, there's the European pulsar timing array. In North America, there's Nanograv. There's new pulsar timing arrays on the block, including in India and China. And here in South Africa, there's the Meerkat pulsar timing array, which I'll talk about at the end. These groups work together as part of the International Pulsar Timing Array to combine their data sets to do the most sensitive searches. Here's just some photos of some of the telescopes used to do these searches. They've got a bunch of different different types. There's big reflectors that are movable, steerable dishes, and interferometers. But the key here is that they're the most sensitive radio telescopes in the world. So around 2020, there's the first evidence started to emerge of this background noise. This is a plot from Nanograv 12.5-year data set showing you the sort of spectral index gamma and the amplitude of this gravitational wave background. And theoretical predictions suggested that it should be around somewhere between like 10 to the power minus 15 and 10 to the power minus 14. So this is the first hints that there could be gravitational waves in these data sets. However, it's possible to detect such background noise when there's none that's present. So this is a plot from a paper published in 2021 showing you, again, the apparent background noise as this blue contours here. But in the simulated data set, there's no background noise. There's just pulsar noise that with the pulsars all having these different values of noise shown here. So what we really need to say is see evidence for these correlations. So 2023 was a real seminal year for the field. There was coordinated searches from all the major efforts that have been going on for decades in Australia, a combined European and Indian effort in North America. And also searches of a shorter data set from the Chinese pulsar timing array, which uses the fast radio telescope. So these, compared to the previous searches that were published a few years before then, the data sets have gone from over 20 years, 15 to 20 years in length, and have used larger samples of millisecond pulsars. The first thing that's clear is that there is strong detection of this background noise. The noise is consistent or modestly consistent between the different arrays. This is a meta-analysis conducted by the International Pulsar Timing Array, and but it's a very strong signal. However, keep in mind that many of the best pulsar timing arrays share common pulsars, so that's the other important thing to keep in mind. However, this was where the excitement happens. When we start to look at the correlations, this is showing you the angular correlation as a function, the correlation coefficient as a function of angular correlation. And what we're seeing here is evidence for these Hellings and Downs correlations. To make plots like this, what you have to do is you have to you're observing 20 to 40 pulsars, and you're averaging together the pulsar pairs in these different bins here. So what you're seeing here now is 2 to 4 sigma evidence for correlations from a gravitational wave background. So this is a very exciting and a very important moment for the field, that we're starting to see the potential rumble of the gravitational waves as they're passing through Earth. One of the interesting things about the signal is that previous constraints on the gravitational wave background were lower than those observed had lower amplitude than those inferred from the signal that we were seeing. So this is a plot showing you what we're seeing in the Parkes pulsar timing array data. The Parkes pulsar timing array is benefited from starting earlier and having access to higher quality data early on, so it is able to produce strong constraints on gravitational wave amplitude early on. And what we're seeing is that in the later data, the signal is significantly louder than it was earlier on. These are 9-year time slices of the gravitational wave amplitude. So this hints that the signal, what we could be seeing, is non-stationary. However, it's also important to keep in mind that the way we analyze the other signals in our pulsar timing data sets could also impact the inferred amplitude. In addition to searching for a gravitational wave background, it's also possible to search for individual sources. And so here's an example of a search undertaken by the Nanograph collaboration, searching for gravitational wave sources at different pixels on the sky. These searches involve doing templates. So you have a model for how a binary supermassive black hole orbits each other and how the gravitational waves are emitted as the orbits harden. And these are the limits you see. While there's no significant evidence for individual gravitational wave sources in this data, once you start seeing evidence for this background noise and hints of the correlations from the signal, it's important to undertake such searches. So really, the gravitational wave searches here were, again, the culmination of decades of efforts. The community is a very cohesive community that's worked together to develop instrumentation for our radio telescopes, undertaken tens of thousands of hours of observing, developed very sophisticated techniques for both doing pulsar timing analysis and then doing the gravitational wave searches with pulsar datasets, and developed a theoretical framework for predicting what sorts of gravitational wave amplitudes we might expect. The results were also very exciting. There's been an incredible amount of interpretation of the results. The properties of the inferred signal have spurred lots of theoretical explanations that both include refining our models for the binary supermassive black hole population, but also speculating on alternative sources for this gravitational wave signal. So this is where we are. That's where we are in 2023. So going forward, we want to make a stronger detection of the gravitational wave signal and understand what the gravitational wave sky looks like. So to do so, what we need to do is observe for a longer time, a larger sample of pulsars, or to a higher precision, or all of the above. So this is where Meerkat comes in. It's a sensitive radio telescope, a very efficient radio telescope. In the same observing band, it's 7 times more sensitive than Meriang. So that means that to get to the same signal-to-noise ratio, it takes 1/49th the time. So this has really been a game-changing instrument in the southern hemisphere for pulsar timing. Pulsar timing with Meerkat for the last 5 years has been undertaken as part of the Meertime Large Survey Project. The project itself has 4 themes. One of them is the Meerkat pulsar timing array, but there's lots of work on studying relativistic binary pulsars. We heard Marissa and Vivek talk about that yesterday, among others. There's globular cluster timing, and there's timing of young pulsars. Meertime has provided pulsar timing instrumentation for Meerkat that's free to use by the community. We've also developed pipelines to do the RFI excision, get rid of radio interference, calibrate the data, and produce the TOAs. And we have a data portal here called pulsars.org.au. And we've really benefited from the Meerkat over the last 5 years. And as of a couple of days ago, there have been 44,333 observations of pulsars undertaken with Meerkat. So the strategy for the Meerkat pulsar timing array has been to time the largest number of pulsars to sub-microsecond precision. We've been doing this roughly every fortnight. And what we do is we tailor our integration times to get the desired precision. So the plot here is showing you a prediction that we made in 2020 about how the array sensitivity should increase with time. So the blue line here is showing you the Meerkat sensitivity. This is signal-to-noise ratio. And you can see here it rises very rapidly with time. it rise roughly t to the power of 13/3 to begin with, which is the spectral index of the gravitational wave background. And that means that despite having a relatively short timing span, it should be really able to contribute significantly to the sensitivity of international gravitational wave efforts, IPTA efforts, very quickly, and also be a very useful gravitational wave detector on its own. So because of the great sensitivity of MeerKAT and the efficiency of the telescopes, you have these small antennas, so you can zip around the sky pretty quickly. You can do this all with relatively modest observing program. So the MeerKAT PTA program is roughly 300 hours per year, and this compares very similarly to the nanograv observing program, which uses roughly 500 hours per year with the Green Bank telescope. So we've been doing an analysis of a 4.5-year data set over the last couple of years, last year or so. It's got roughly 250,000 TOAs in it. There's more TOAs here than I said in than observations because we take the data and we subdivide the data into different wavelengths when we do our analysis. And we do that because what we need to do is understand what other noise processes could be in our data set. Our data analysis uses sort of the standard techniques that were used in the 2023 searches. The one difference is that we've been searching for a larger range of noise sources in our data. These are the astrophysical foreground sources to a potential gravitational wave background. So this plot here is a bit messy, but maybe that's by design. So you can see here that this is models of the different noise processes in this pulsar. So you can see here, this is the best pulsar again. So it's got noise from the interstellar medium, noise from the solar wind, and also achromatic red noise. And I argue that this is a gravitational wave. If I zoom in on it, this is what it looks like here. So this is gravitation. If this is gravitational waves, it's got peak-to-peak amplitude of a few hundred nanoseconds over the course of 4.5 years. I presented at the IAU in Honolulu on gravitational wave searches. I don't know if some of you remember this. And I presented this data here. This is the same pulsar. It's got 50 data. I've had to average together the Parkes data to reduce the noise. But you can see here, it's looking a bit different now than it did then. So if it is a gravitational wave, it's a background it's a signal that's very unusual. So to put it, this is again the plot from the PPTA data. I've gone and put it into pgplot here, and you can see here where the MeerKAT noise amplitude compares to that. So, of course, what we want to see is the spatial correlations. So when we use models chosen using our detailed noise analysis, where we do the noise analysis pulsar by pulsar independently, this is what we get for the spatial correlations. So the green again is showing you the expected Hellings and Downs curve, and the blue is the data. So there's visually apparent Hellings and Downs correlations in this data when we use these noise processes, and when you assess the significance of it under these assumptions, it's roughly 3.4 sigma, so it's comparable to the results for the other PTA experiments. Things are a bit complicated, though. So when we choose alternate noise processes, the significance can go down. When we for example, when we use add intrinsic rotational noise to all the pulsars, and also when we account for the covariance between our noise modeling and covariance in our noise modeling, and also especially when we do the sort of additional background bootstrap or scrambling. So the story's not finished yet with the MeerKAT data analysis. So really to confidently detect a gravitational wave background with MeerKAT on its own, we need more time. We know that the gravitational wave sensitivity should increase very rapidly with time. I'd argue that there's a real opportunity to improve our data analysis in terms of how we do the noise modeling. But excitingly, what we can also do is combine the Meerkat data with those from the other projects. And that's under the IPTA project, and that data set has been provided to the IPTA for such searches, which will be undertaken in the next year. One of the exciting things we can also do is, again, look to see if the gravitational wave background is isotropic or not. Again, if a background is cosmological, we'd expect it basically to look the same in all directions. Whereas if it's astrophysical, meaning it comes from binary supermassive black holes, we might expect there to be hotspots here or there. With its large number of pulsars, that means we've got a lot of baselines in our gravitational wave interferometer, so we have really high spatial resolution with Meerkat. We've undertaken augmented gravitational wave map-making approaches that were developed by LIGO and transported them into PTA work. And this is an example of a map made by students Catherine Grendel and Rowena Nathan at one particular gravitational wave frequency. There's an interesting hotspot here that's got a significance of 0.02. Nothing to write home about, but this is showing you some of the things that we can do with the map making as we go forward. So in addition to making nice maps and seeing what the gravitational wave sky looks like, which I'm particularly excited about, I think these techniques are also going to help us understand our data sets better. If we start seeing really big negative cold spots in our data, that's going to tell us that, oh, maybe there's something wrong with our pulsar timing modeling. So there's a bunch of other talks in the symposium on pulsar timing arrays. I'll pass through this quickly and just get to my conclusions. So PTAs are alive. We've had a step change in transition from detection, and we're moving into the era of studying the nanohertz gravitational wave universe. So the large number of pulsars that we're now timing enables us to do sensitive searches for gravitational waves and searches for individual sources. So the international combination efforts are going to be key. Meerkat itself is poised to make a foundational contribution to the field, and the SKA is also going to make great efforts. So I just want to emphasize that the important role that Meerkat in South Africa has played in this field and will continue to play over the coming decades. Thank you.
Thank you very much, Ryan. And we have time for questions. Paul, please. Can we get a microphone in front?
Yeah, stay tuned.
Thank you. Fantastic talk, Ryan, and I'm so excited to see all these results coming through. I had a question. In one of your first plots, you showed your best pulsar, right?
Yeah.
And the timing residuals that you had from that, and you said, well, this is the pulsar doing stuff.
Yeah.
And then later on, you said, well, maybe it actually is a GW. How do you make the difference between those two?
Yeah, that's the million-dollar question, really. What you need to see is the angular correlations. You need to see see the effect of that pulsar. If I look at a pulsar that is 90 degrees away, it should be doing sort of the opposite thing. And it shouldn't be, it's not going to be one-to-one like that. You're going to have to sort of statistically average, like pulsar, the pulsar should show this angular correlation.
But that's only when it's a gravitational wave that passes by Earth, right?
Yeah.
But if it's a gravitational wave passing by the pulsar,
Yeah.
right, then you would still see the effect in the pulsar
Yeah.
itself. In just that one.
Yeah, exactly. And that's what we call the background noise. I think one of the interesting things that's been seen in a lot of the data sets is that when you look at the pulsars individually, they all show noise that has roughly the same statistical properties. And then when you do the joint analysis, that noise all gets identified as the gravitational wave background. So there's some very nice papers from Nanograv that show this effect. But yeah, you're right. The signal that I see in the best pulsar is quite weird. I think, I mean, the fact that the pulsar is doing something different now than it did 10 years ago is a very exciting thing that we need to look at and understand it in more detail. But the fact that the amplitude of the gravitational waves, in data sets, from 10 years ago is different than the data sets from now is also very interesting and a very exciting thing to understand.
We have a question over there, please. Sorry. In the center. Yes. Thank you.
Given the expected increase in sensitivity with Meerkat and SKA, can you say anything about when you expect to begin to see individual sources?
Yeah, that's it's a very interesting work. It depends a lot on if there's sort of very massive binary supermassive black holes nearby. There was some interesting work by the group of Alberto Zazana that was just published a couple of weeks ago, which was looking at eccentric sources and suggested that within the next, say, 4 years, we should be able to start seeing eccentric sources. There's more optimistic forecasts as well. And one of the exciting things people like to do is to go look at, periodic AGN, for example. And so if you start seeing AGN with periods of 8 years, is that a gravitational wave or not? And then what you can do is you can now say, I'm going to point my pulsar timing array in that direction and do a very sensitive search in that direction because I don't have to do a unbiased search for the entire sky.
So thanks very much again, Ryan. I think we'll have to stop the questions here. Just a quick reminder that for those who want to continue to hear the exciting talks from IAU 389, we're starting today at 11 o'clock, so we have an extra long break for looking at posters this morning. We're starting at 11 in Auditorium 2. But before we stop, let's thank all of the speakers in the session again for wonderful talks. Thank you.
participe. Ayude. So just a quick note that we are waiting for people to trickle in. People are, of course, still coming out of their other meetings, so we'll start at 12:15. That is the starting time. For those of you who are just coming in, welcome. We'll start the talks at 12:15. Good afternoon, everybody, and welcome to this session, this lunch talk session on the prize winners from the Outreach, Development and Education Prizes who will present their work, the excellent work that they have been doing here in this meeting. Now, we had a fantastic opening ceremony yesterday, and during that, we already introduced all the winners in quite some detail. So I will be very brief here in the introductions, and I suggest that we actually go straight to the talks. And we do that in the order of O, D, and E. So we actually start with outreach. And Saran Poshirchinda from Thailand, who has done all this wonderful work in Thailand on putting Thailand on the map in terms of outreach, will be our first speaker. Saran, please come up to the podium.
Okay. Ladies and gentlemen, esteemed colleagues, and honored guests, away. Well, I'm deeply honored to be here today to receive the ODE Prize in Outreach from the IAU. This award is not just a recognition of my work, but a testament to the power of dreams and the unwavering pursuit of a vision. Let me take you back to a pivotal moment in my life. As a young child, I spent a lot of time during the summer by the sea, always amazed by the sight of the stars under the dark sky. And in 1976, I had a chance to borrow a telescope, a small telescope from my uncle. Without knowing much about the sky, I turned the telescope to a fairly bright star to the west, not high above the horizon. Then I noticed that the star seems to have a ring around it. That was when I saw Saturn through a telescope for the first time. The rings of Saturn, so distant yet so vivid, ignited a passion in me that had burned brightly ever since. A couple of years later, I was fortunate to receive my own telescope as a Christmas gift from my father. I began to explore other objects in the night sky, inspired by regular visits to the Bangkok Planetarium. However, many others in Thailand were not so fortunate. At the time, most people in Thailand had not heard about astronomy, let alone seen a telescope. Astronomy outreach, if any, were largely dependent on imported books written in other languages. There were barely any professional astronomers working in Thailand at the time, and pursuing a career in astronomy was not an option. So I pursued another science career, but never let go of my keen interest in astronomy. However, deep within me lies a dream that perhaps one day another kid in Thailand who was touched by the same passion would have an opportunity that I never had to pursue astronomy, not just as a hobby, but as a viable career. Then one night in 1997, as I was observing the comet Hale-Bopp with my fellow amateur astronomers, the transparency and extremely dark sky on the summit of the highest peak in Thailand rekindled my dream for an astronomical infrastructure in the country. Not long after, in July of that year, NASA successfully landed the Mars Pathfinder spacecraft on the red planet. And due to the lack of any standing astronomical institution in Thailand and the lack of coverage from the general Thai media, I was called in to give a briefing on the mission to the Minister of Science. And after a long discussion, he asked me what we should do to develop astronomy in Thailand. And I told him of the potential to host the first national observatory on the highest peak in the country. His response was, "Why don't you go and wrap up a project?" It took us many years of ups and downs, but almost 7 years later, the project was approved in 2004. We realized that without any governing body dedicated to astronomy, the observatory would not be successful. And establishing NARIT was not just about building infrastructure, It was about creating a movement. The challenges were immense. We had no experienced staff, no established programs, and no hope for public support. Most people have never even heard of astronomy. We recognized right away that filling that gap in public awareness in astronomy is not only the key to our success, but it is also our responsibility and a huge opportunity to leave a lasting impact in ways that could transform Thai society like no other could. And upon becoming a full research organization in early 2009, we started an extensive outreach program right away. Because we lacked the usual outreach infrastructure available to many developed nations, we have to fill that gap. And NARIT must serve as science communicator, planetarium operators, educators, and everything that's missing. We train our staff to have experience and skills in stargazing and astrophotography. We instilled a culture in our team to respond to all requests, no matter how big or small. And every kid we interacted with is treated as VIP guest. We were driven by the belief that every individual deserves the opportunity to experience the wonders of the universe. At NARIT, our motto is, leave no one behind. This is not just a figure of speech for us. Our ultimate outreach initiative aim is to reach every single person in the country. We built not one single planetarium, but many smaller ones, so we can be part of the community. The public must have access to the latest astronomical news in their own language. As such, our team covered every major and minor astronomical discoveries and events in the past 15 years. We hold astronomy camps after camps. We set up telescopes in shopping malls, in markets, and at every astronomical event. I was one of the very few children in Thailand who had the chance to see Saturn through a telescope. And it leaves such a lasting impact on my career in science. Imagine the impact we could create if every child could get that experience. We believe that astronomy outreach is not just for ourselves, not just for astronomy. It is a way to inspire scientific curiosity and technological advancement across the nation. Public outreach has always been part of NARIT's primary goals. We allocate significant resources to it, and we are proud to have one of the largest outreach teams in the world among research institutes, with over 60 staff members. However, none of our outreach staff are astronomers by profession. We recruited our staff members out of their passion for astronomy, regardless of their degrees. Our primary target groups include students, teachers, the general public, and amateur astronomers. And despite allocating a larger percentage of our budget to outreach than most research institutions, it is still only 5% of the operating costs. However, when you reach the scale that we have, our work has a potential to reach a large number of people. In the last fiscal year alone, we reached nearly 700,000 participants, approximately 1% of the Thai population. Soon, this number is going to surpass 1 million participants every calendar year. More than 2/3 of these are children of school age, and about 2/3 of these are girls. We strongly believe our outreach model is a success story in which outreach efforts can support research infrastructures. With our increasing success and rising public interest in astronomy and science outreach, our stakeholders and policymakers also recognize the importance of science and astronomy. This has allowed us the vital momentum that propelled our research budget forward in the early years. And currently, NARIT is home to 33 researchers, more than 100 engineers, and operates the largest optical and radio telescopes in the region, along with 5 robotic telescopes in 4 continents, as well as collaborations with many institutions around the world. This could not happen without the strong support from the public we interacted with. With the scale at which we engaging with the public, we only need about $1 for each participant, and it will be more than enough to cover the outreach expense each year. But keep in mind that 15 years ago, we started from 0. All it needed was the commitment to take that first step. And the IAU has set a goal to encourage research institutes to spend 1% of their budget on outreach. Imagine where you could be 15 years from now with just 1% of your budget dedicated to outreach, and how vital those public support could be for your next projects. Going back 15 to 20 years ago, we would never have imagined any of this to happen. I imagine we would be very lucky enough to have one regional observatory for the public that survived all the management nightmare, let alone having regular visitors filling 50-seat planetarium on the outskirts of Bangkok. Now we welcome over 200,000 visitors annually in all our planetariums combined. Our social media has 700,000 followers. And last year, we held the largest stargazing event ever recorded by mankind, as 12,500 visitors gathered at a park in a single night, lined up to look through our telescopes for the event held in Bangkok. As we look towards the future, our goal has always been to act as a catalyst and create an environment which enables natural outreach initiatives to flourish. These include hundreds of activities each year, such as astronomy camps, preserving the night sky, stargazing for the public, astrophotography contests, and many more. However, this would not mean much if our work is not being propagated forward. Probably the most important aspect of our outreach lies in training those who can train the others. Teachers remain one of our most important target groups, and our teacher training workshops have inspired over 9,000 educators over the years. We continue to look for ways we can support them, so we can launch a program. So we have launched a program where we provide 10-inch Dobsonian to schools in need on loan for free of charge. Currently, there are over 610 of these telescopes scattered all over Thailand. If there is a star exploding in the night sky right now, through our teacher network, we can organize a nationwide observing campaign by tomorrow night. As more and more people begin to offer their own contribution towards the outreach effort, we can now switch into a more supporting role. We can leverage our position as the recognized national institute to coordinate outreach efforts. We have conferences for teachers and students, to which we can offer incentives to those who would like to start, and awards for those who have done amazing work. We can promote astrotourism by certifying dark sky areas and provide certificates for astro guides. We have found that astronomy has a power to inspire and transform people in ways that few other things can. Perhaps this is best demonstrated by stories of some people whom we have touched. A small kid who was once our regular visitor is now a prominent science influencer, working tirelessly to inspire those after him. A 90-year-old grandmother who, for the first time in her life, realized that the moon is full of craters. When she looked through one of our Dobsonian telescopes, a teacher who trained with us brought to a remote mountain in the countryside. A former delinquent who spent her early college years on motorcycles and nearly got arrested for stabbing a guy with a broken bottle, who later discovered her passion through astronomy and managed to turn her life around after an internship with NARIT. She's now working in one of our regional observatories and dedicating her life to providing opportunities for those less fortunate. A student from a poor illegal immigrant family who gave up on school has also found his passion through her work and they decided to continue to secondary school. These are just some of the people whom we managed to touch over the years. I would like to share a deeply emotional video titled Astronomy for the Blind. This video encapsulates our mission and the profound impact of one of our outreach initiatives. It illustrates how we strive to ensure that astronomy leaves no one behind. While we certainly have reached many, we must continue to seek new ways to reach those we have yet to touch. Well, I must thank the ODE Prize Committee for this incredible honor, Professor Michael Bode for nominating me, Dame Jocelyn Bell Burnell and Dr. Busbah Kramer for helping to support my nomination, also my family for their support through the years, and my dedicated outreach team who believe in our mission to transform Thailand. Let us continue to inspire and ignite the passion for astronomy in every corner of the world. Thank you very much. Any questions?
Thank you so much, Saran, for this very inspirational presentation. Fantastic what you have accomplished in Thailand in these years.
Thank you very much.
We have actually time for a couple of questions. So please, go ahead, ask questions. Please. Yeah. Yeah, we'll get a microphone.
Hello. Everything you shared was amazing. That video was really great to get to see a lot of the hands-on activities you developed. Do you have more information about those resources available on a website, or are you sharing those with other education and outreach teams?
Yes, the video is shared on our YouTube channel. I can give you a link, yes.
Can you say a few more words as to what caused this very steep increase as of 2021? What did you start doing differently in 2021 to reach all of a sudden a much larger fraction of the
I think that the opening of our public observatories across the country, yes. Now we operating 5 of them, 4 regional observatories, including our headquarters in Chiang Mai, Thailand. That's why the steep increase. But I think also now the interest in astronomy in the country is getting very, very high indeed. And I think most of the kids, students, and teachers aware of now it.
Right,
yeah.
right. And you have also very much support of the Princess Sirzan.
Well, we have, she is the power behind
I
us.
definitely the power behind that. Yeah. Okay, is there any other questions still in the audience? Yes?
Yes,
Go ahead.
please.
Yeah, you just took a word out of my mouth. I was trying to mention the princess, because when you visit Chiang Mai, the princess is in everybody's mouth, and she's very supportive of science, and that was a real pleasure to see. And congratulations. This movie was spectacular, you know.
Well, she is...
Astronomy for the blind, wow.
Yes, and we've done this activities for the blind so many times. The last time was just a couple of weeks ago at several locations, yes. And if you notice in the last part of the video, you know, the blind students looking through telescopes, you probably wonder why or how they can see the stars. Actually, they can't, but they just like to have experience. And some of them, you know, 70% of the blind students can still see some light. Many of them told me that they could distinguish between the bright light of the moon and light from Saturn and Jupiter. Yes.
One final question.
Hi. I have visited Chiang Mai in 1995 when the total eclipse was occurred in Thailand. Is there any such astronomical event using for outreach?
Oh yes, we are organizing one conference towards the end of the year. Last week of November this year, we are going to organize first time we call South Asia Planetarium Education and Outreach Symposium. Yes, in Chiang Mai, Thailand. Yeah, you're very welcome.
Excellent. And I really like the motto of every kid is a VIP. That's a very beautiful motto as well. Thank you so much, Saran.
Thank you.
Okay, then we move on to the developments and to Sensa Bridge. We have a foursome of winners there, and they are going to give the presentation. The floor is yours.
Thank you all for being here in person and remotely. Today, we're going to talk about several years of work done at the Central American Caribbean Bridge in Astrophysics, or CENCA Bridge for short. This work was done by 4 people. Myself, I'm Antonio Porras Valverde from Costa Rica, and currently I'm a postdoctoral fellow at Yale University in the United States. We have Gloria, Vale, Valeria, and Jaira, who are from Nicaragua and Honduras, and they will be introducing themselves shortly. CENCA Bridge is a nonprofit organization established in 2022 in the state of Tennessee in the United States with the mission to create and develop astronomy research opportunities in Central America and the Caribbean for marginalized students. But CENCA Bridge did not just become a nonprofit from one day to another. It actually, the effort started in 2016, and we'll take you through the journey of how it started and how we are now, where we are now. So when I started this, I was starting my master's at Fisk University in the United States, and I realized that when I left Costa Rica at the age of 17, I left because I did not have any opportunities to do astronomy research in my country. And so when I started this program, I recruited 6 people from the University of Costa Rica and started mentoring them to teach them about astronomy. And I developed a webinar series where every month I would invite Latin American speakers to come give a talk about their research in Spanish, but also give a sense of their academic journey. And to me, that was important because representation was something that we were lacking and that we have lacked until this program began. Personally, I always have had a hard time just doing scientific research because I don't know how to respond to people when they say, how does this relate to us, the public? So I generally believe that anything that we do, it has to impact the community directly, and therefore I have this motto that one cannot prioritize scientific discoveries without acknowledging the humanity of the people we work with. Okay.
Okay, so we just heard a little bit about Antonio's personal motivation to start this program, and I will forever be grateful to them for doing this since it has been life-changing. But some other motivation. So there are no PhD programs in astrophysics in the region. There are a handful of countries in Central America and the Caribbean that do have a master's degree, maybe in physics. But there's a very diverse set of countries that we're serving, so the access to education in astronomy or just science in general is very different depending on the country. There's also no sustainable infrastructure for growth. This can refer to facilities like telescopes, but also funding, since there's little to no governmental financial support to pursue science. And there's also something that we care deeply about, which is who gets to be an astronomer. So even those of us who do get the chance to pursue astronomy, we may not be representative of the actual marginalized communities in each of these countries. But a little bit about myself. So I'm Gloria Fonseca Alvarez. I'm a postdoc at NOIR Lab. I am originally from Nicaragua. I left home when I was 15, not to pursue astronomy, but for other reasons. But one thing that I have encountered as I am pursuing astronomy is that I feel like I lost access to my community. Until I met Antonio, Valeria, and Jaira and all the Senka students. We met actually online late 2019, and this allowed me to have access to a community that was not available to me in my immediate surroundings, and that has been incredibly supportive for me and also for each other. But one thing that is useful about the fact that we have a completely remote program is that we can serve as a bridge to take resources that are available in where astronomy is more developed and connect that directly to students in institutions in Central America and the Caribbean where astronomy is not as developed. Right? One example is the remote internship that we have, where we connect students in those institutions to advisors to do a project in astronomy for a few months, and they get to do that at home. Right? We also provide workshops and other things. But also, another important thing is that we all have very similar experiences, being Central American scientists outside of our home. And we have come together and taken our experiences to create a shared vision of what we believe astronomy should be as far as inclusion. But yeah.
So like Gloria mentioned before, despite the hardships, we found that students are actually very passionate and very eager to pursue astronomy, even with all the obstacles they have to encounter. And this is very clear when you can see the community impact that we've had. So for example, we guided 5 students to start graduate school outside of their countries. Some have attended summer schools and internships abroad. Some of them also, well, a lot of them go through workshops and webinars, and even 3 students have started their local leadership programs. We also were awarded 21,000 euros for 3 years from the IAU GA. Thank you very much. And that was very amazing for us to have in order to provide some economical relief, which I think equates to a bit more accessibility in astronomy. So a little bit about me. Okay, there you go. I am Valeria Hurtado. I am from Nicaragua. I became a co-lead in 2020, and something that that was very important for me was going through my career and feeling like I had to split myself up into astronomy and my full self. And so I found out that through, once I met Gloria and Antonio, it was very critical, it was very life-changing for me to not just meet astronomers that are from like a similar area, but people that are motivated to like give back to the community. And so once we became friends and we felt very comfortable with each other, we asked ourselves the questions, how far can we go together? And how can our experiences shape what Senka Bridge is? Because we've had some similar bad and some good experiences. And so we wanted to make sure that Senka Bridge is a great experience for the students. And so some of our work together included applying for a proposal just for fun. We weren't sure where it was going to go. And then surprise, the IAU GA granted us money for 3 years, as we mentioned, which was amazing. And so just to end this bit here, I think something that sums this up is, if you want to go fast, go alone, but if you want to go far, go together.
Well, something that is important for us is the community. I think you have listened to much that were in our presentation. So we highlight community, and Senka Bridge is not only made of us, part of us, the co-leadership team. We also are built of mentors. We have created a huge network of mentors. They were students in the internship at the beginning, and right now they are mentors. They are from different part of the region of the Central American and Caribbean. And if you look the picture, you will see me, because I began as a mentor. Hi, my name is Jaira Mendoza Moncada. I'm from Honduras. And also I am known as the result, because I began in Senka at 2020. I joined Senka as an internship student, and I began my Journey in Academy career. I worked in that year, I worked with a professor from the Universidade Federal do Rio de Janeiro, in Rio de Janeiro, Brazil. I work in the astrochemistry area, and in 2021, I became a mentor, and I share my own personal experience as a student. I became a mentor, and I can share my experience as a student with other students, hoping that helped them to get through the internship. So in 2021, I moved to Brazil, because I began my master's degree. My advisor is the professor I met in Senka, so we can say that the Senka accomplished one of the objects. I left Honduras, I left my home to pursue academic career. Currently, I'm finishing my master's degree. I work with her, the professor from Rio de Janeiro. And the same year, 2022, I joined the Senka. I joined also now. I am a co-lead, so in that year I joined. Sorry, I'm a little nervous. Well, Senka gave me the chance to begin my career. Is the object to let the people, give the people the opportunity to begin the career. And so I'm so thankful for the Senka. Senka is a project that I love so much. And they gave me the chance to begin, and also thankful to Gloria, Antonio, and Valeria to open the door to my academic career, and also open the doors for me in the co-leader team. And one thing that I want to remake is, as the IAU president, Deborah Elmer-Green, said, astronomy is for all. And that for all includes Central America and the Caribbean region. We can't forget the people from that region. We can't forget us. We can't forget them. So with that, I want to talk about the infrastructure impact of CENCA. CENCA is the only program in the Central American and Caribbean region that is providing a paid remote internship, mentorship network, and also international network of undergraduates from the region in astronomy. CENCA opened the door for the people and let them meet the professor out of the region to begin their career. And CENCA have created opportunity for 39 students to participate in astronomy research. These 39, those are CENCA alumni, but right now we have 9 students that are currently in the program. So almost 50 students are part of the internship were part, and right now they are part. And 11 of them have become mentors in 2 incoming remote interns.
Okay, so what now, and what does this have to do with you? I think it has a lot to do with you, because this work and our achievements have been done by the community for the community. We would not have been able to do this by ourselves. And so if you were inspired, or if you feel like you've been wanting to do something similar or something maybe even better than this, how do you build your own community? And so, as I mentioned before, we first met by chance. We ended up having similar interests and similar stories. And so you might have started this step already. Your friends, your family, peers could be part of this community, could be the group that you start something new with. And so it can be people that you feel comfortable with. You can ask your peers, hey, like, what do you care about? And you might end up caring about the same thing. However, if you feel like this is maybe a lot, I mean, you don't have that much time, and you would rather be an ally, how can allies help? And so I can give an example about how allies have helped us through our own career. So for example, when we submitted our proposal to the IAU GA, we did not do this by ourselves. We had help from people from the Fisk Vanderbilt Bridge. Also, the National Radio Astronomy Observatory has helped us a lot, even just something as like small as a Zoom membership. That's where we hold our meetings, and RAO has been providing us with the funding to host those meetings. Besides some of these examples, if you feel like you would like to join CENCA, you can absolutely do so. You can become an advisor. And feel free to come by. We don't have yet business cards, but we will soon. And so you can ask us for our email, and you can come up to us and sign up to be an advisor. But anyways, just to end this, I think a lot of the people here in the IAU will agree. We hope to see a future in the astronomical field where, regardless of where you're from, people can have the opportunity of doing science in community.
Sorry, we're not done. Yeah, so I'll go quick. So you just heard a very brief overview of our program, but just to recap, we started in 2016 with just doing webinars with Antonio in just Costa Rica. Then we expanded to Honduras and Guatemala. We started a remote internship program that now covers pretty much all of Central America and several countries in the Caribbean. In 2020, several of us joined forces in order to make this program more impactful in more countries. We worked together to get an IAU OAD award. And then in 2022, lots of exciting things happened. Jaira joined. Many of us moved forward with our careers, and we were able to see just how much impact CENCA had, not just on the community, but also ourselves and our future. And we're not done still.
And so all of this came to what it is today and this conference. And what's so amazing about all of this is that we all came together in this conference to meet each other for the first time in person after working together for a lot of years. And so this is a very unique program in that sense, that we were able to work with each other remotely and make the impact that we have made. I would like to acknowledge the National Radio Astronomy Observatory and the IAU ODE for the prize, as well as the ODE Prize Committee and EON for also the opportunity for us to be here. Thank you.
Fantastic. Thanks so much for sharing this story, and I hope it will still continue, go very far. I really like that African proverb that's put you on the path to go even further, long-lasting. Good. Time for a couple of questions. Who would like to join? Yeah, we have a question over there. It comes from the...
Thank you for sharing. I have a question. How did you advertise the program for fine students, etc.?
Excuse me, could you repeat that? Sorry.
How did you advertise the program?
Okay. Yes. Through the students. The students know best who to suggest this, and I feel like when we can surely advertise through the departments and the professors because we have connections there, but we believe that those advertisements could be biased on who the professors and the people are going to be advertising this to. And so because we want the marginalized communities, the students and their peers are the best people to advertise. So we already have built a very big community where the students can then know about each other and so on. Yeah.
All right. Good. Let's see. Any other comments, questions? It's difficult to see in the back in the dark. Oh, there's one more. Yeah, go ahead.
Hi, thank you. What would you say is your biggest challenge going forward, like from 2024, and how are you going to overcome it?
Great question. So I guess one thing that we might not have explicitly said is that we started we were all grad students. Now we are 2 postdocs and 2 grad students and no time. So we always made time for this because we really care about it. We have our careers also doing research, doing other things that we really care about. So I think time management, as we grow, we want to do more things. We want to continue doing the impact and even more impact. And another direct answer is money. We need money. So I think those will be the 2 challenges, is managing our careers while doing this the right way.
Good. I don't see any other hands. So thanks again, all 4 of you. And all the best with Senkabridge and raising the level of astronomy in your region. As you said, you are being put now on the map. You're doing that yourselves. It's fantastic to see this effort appearing. All the best.
Thank you.
All right, and we got to the final part, the E of education. And here we have our duo. After our quartet, we now have a duo. We have Linda Strube and Bonaventure Okere, who are going to tell us about PASEA. That's all.
Our way. Thank you very much for this opportunity. Bonaventure Okere. Though some call it Bonaventura, it depends on the part of the globe you come from. You can actually anglicize it or italize it anywhere. So often I'm referred to as Bonaventure Okere. And I work with the National Space Research and Development Agency, NASDA of Nigeria. NASDA has what we call activity centers, center created for different field of space research and development. And I'm actually the director of the Center for Basic Space Science and Astronomy in Nigeria. I'm also the regional coordinator of the West African regional office of astronomy for development created by IAU GA. That office is domiciled at the Center for Basic Space Science. Our duty is to use astronomy to create development, stimulate development, and at the same time, develop astronomy. So we have been doing this work for some time. Actually, on my own person, somebody may ask me, why interest in astronomy, despite where you come from? My interest in astronomy is based on curiosity. After my graduation as a physics graduate, I got a job with one college of education. And in that college of education, they have the Department of Integrated Science. And they asked me to take 2 courses in integrated science. One course is the moon and the earth, and the second course was the universe. In the course of delivering these lectures, I began to understand that the sun or the stars we see in the sky is not as I saw it in the books. I began to see the sun as far bigger than the earth. I was wondering, how can this big object there still hang there? As a child, I saw the sky as a ceiling. We had this just point of light just placed there. So when I read about the sun and the stars more, I became very curious, and I decided that I must find out about these objects. And that's why I pursued a course in post-AGB B stars. I studied the evolved stars, how they are born and how they die. So I think I'm a star mortician. So I know how the stars are born, and it became very curious to me. That's why I picked interest in astronomy. All right, coming to PASEA, this talk is going to be kind of in 2 phases. I'll introduce myself, give an overview of PASEA, and then Linda will take us through. She will introduce herself and give us an overview of her role in PASEA and how we'll come to really carry out that project. Now, the PASEA is an acronym for the Pan-African School for Emerging Astronomers. And it is designed and taught by a collaboration of astronomers from Africa, North America, Europe, Asia, Australia, Canada. So we have a team of volunteers, and these instructors are volunteers. Nobody pays them anything. We try to raise funds for them to see if they can come. A lot sacrifice their time and their money to come and teach the younger ones. Now, the question is, what is the vision? What do I intend to achieve by this? Now, we recall that in Africa, which has almost become the home of astronomy instrumentation, we have the SKA, we have the MIACAT, we have the SOT, we have the SAL, we have Institute Observatory, we have the one in Burkina Faso. Now, what role shall African students play? How do we make them involved and be part of this terabytes of data being collected from these instruments? So that's the quest. We now start thinking, we need actually have to build a critical mass of astronomers in Africa. And how do you go about this? There's no institution hosting it. There's no government body hosting it. How can we go about this and achieve this? And that is where we come. We said we need to contribute to building the community among African countries, community of astronomers. How do we encourage them? I remember when OAD was formed in 2011, I was here, that my first one coming to Cape Town. We were here. We were trying to define what OAD means. Office of Astronomy for Development. Now, for development, trying to use astronomy to create development and also see how we can develop astronomy. And we realized that you cannot use astronomy to cause development without developing astronomy. So we have to develop astronomy first of all. And that is where we come. And this group of people, when we gather, we share ideas, we form a community of astronomers beyond Africa. Now, how did this idea come about? And that's a question that I bother many people. How do we come about idea of the PASEA? Actually, at the beginning, this idea was given birth in Beijing, IAU GA in 2012. I made a presentation, I made a case for IAU to grant Nigeria to host the West African Regional Office. After my presentation, Mike Ray from University of Toronto then staged a meeting between me and him. He saw me, say, come, Bonaventure, let us have a meeting. I've been eager to get somebody from Africa who can help us bring African students to Canada because they run summer school then. But the problem is, we can only take 1 or 2 African students. How can we get more African students? Then we begin to rub ideas. How can I hold this school in Africa instead of coming to Canada? Because it's more expensive to bring students from Africa to Canada. We now start thinking of how to make it happen in Africa. So after that encounter with him, I had a meeting with Professor, let me point them out. Yeah, there is Johnson Orama, who was there that day. James Chibeze, who's in South Africa now, was there at the meeting. Dr. Anthony Obi, Linda Struve. You can see Mike Reed is the one at the extreme there. That's Mike Reed. And that's Ike, this is Johnson, this is James, this is Linda, and that's my very self. So after that meeting with Mike Reed, we now met and said, no, let us organize this in Africa. And that time, it came up as a West African school for, we call it West African International Summer School for Young Astronomers. It was only for West Africa, because we could not go beyond West Africa. Where do we get the resources? When we began this school in 2013, it was initiated in 2012. By 2013, we had the first edition. And during that first edition, Linda came. There were 4 instructors from Canada. Most of them were postdoctoral students at University of Toronto. Linda July Zhang, she's from Australia. Heidi from America, and Kelly from North America, if I'm right. So 4 of these ladies came to Nigeria. I hosted them. But good enough, OAD brought key into this project. They gave us some little cash fund to start this program. And we were able to manage that cost from the little we get from our office, from NASDAQ, and then we had a first edition in Abuja in 2013. And then at that meeting, we agreed that we're going to hold the school biannually. Instead of making it annual, I used 1 year to prepare source of funds. The second year, we host it. And then the 12-15 again, we did it in Soka, my own institution, my own center hosted them, we did it. And mostly the person were from West Africa, Ghana, Senegal, and Sierra Leone. They came. Then we discovered that the next edition, Ghana opted to host it. We took it to Accra, Ghana. And there, we discovered that more African students were interested. It's no longer particular for West Africa. Other students from other African countries indicated interest to participate in this school. Then we now start thinking. Then after discussion with OAD and AFAS, I discovered that if we wanted to be an African thing, we had to change the name from West Africa to make it an Pan-African. We began in Ghana to discuss how we can make it a Pan-African instead of West African. So in 2019, we made it a Pan-African school to comprise all African countries. And now what we do is we advertise this school, asking any country that's interested to host. Now, the advantage of hosting it in a particular region is most of them from that region participate because of cost. And in each country we host it, instructors from that place also trained on how to carry out this school. Linda will talk about how the school is being organized. I will give her the opportunity to do that. So that's how we have done this school. This year's one is going to be the 6th edition. I had it for 5 editions. We now began to move from one region of Africa to the other. The last edition was in 2022, which took place in Zambia, Livingstone, Zambia. It could have been in 2021, but because of COVID-19, we could not host it in 2021. We now moved to 2022, and it was in Zambia. So at the beginning, you can see here it was located only within the West African region, and after that, it expanded to other African countries. It started going gradually, and this year's only going to be in Tunisia, Mona still, and we hope it's going to actually take place, and already the plan is on ground. Now, what happened in the past is that we formed what we call a teamwork co-directors, those who are virtually regular in all the editions of PASI. And you can see my very self there. You see Linda in the middle, and Jilai Zhang from Australia, and then Professor James Chibeze from University of South Africa. So we 4 of us formed a team of directors that share responsibilities. We can raise funds, organize transportation, advertise, and then see how we can make this work. It's been very challenging, really. This actually gives an idea of the distribution of participants. So far, we started it across Africa. You can see within the Eastern Africa, Western Africa, Northern Africa, we are going. So we want to spread this across Africa. So at the end of it all, we must have achieved encouraging people to take interest in astronomy and at the same time develop critical mass astronomers in Africa. This school we have been running couldn't have been successful without people collaborating with us. And I want to just mention some of these. At the beginning, I mentioned University of Toronto, ICTP, and there's a role IAU to play for us. Like ICTP, if they're giving us little, the fund they're giving us, they don't pay the money to individual accounts. We normally beg IAU, give us your account. They pay into IAU account. From there, we do our business, we do with it. And then we have the African Astronomical Society, which actually was dreaming or thinking of being the home for PASI. We wanted AFAS to be the host for AFAS. They've been supporting us immensely, seriously. And another body that's supporting us very well every session is OAD. I don't forget that. There is no session where we are going to do that they don't give us funds to actually bring students together. We know it's a fund to bring, transport students, accommodate them, feed them. The school is such tough in terms of funding because we have to what? Transport students and instructors, feed them, accommodate them for a period of 2 weeks. And the 2 weeks, 1 week for the teaching, and 1 week for kind of workshop for instructor, because the local instructor also had to be trained the method, because the method of teaching PASI is different from ECA method. ECA, because when we were forming PASI, we thought that IAU had the ECA, but ECA program is mostly for postgraduate students, those already doing astronomy. But UNA said no, we had to incorporate teachers, undergrad, those who are not even doing astronomy at all, to encourage their interest in astronomy. So because of that, we have a week workshop to train those who are there. So we have the Sarao, we have the NASDA, my major agents, we have DARA. They have been actually supporting us each particular session we are doing this program. So at this point, without wasting more time, I want to call on Linda, my partner. She has been very supportive. She's always there. And it can't be a better partner than Linda. She has been the best I've ever had. Yeah, so I will call upon her now to take out the next stage of this presentation. Thank you. I'll stand and wait.
Thank you, thank you. Thanks, everyone. Yes, thanks, Bonaventure. My name is Linda Stribba, and my personal mission in my career is to help people around the world to feel joy, love, empowerment, and community through astronomy and physics education, to feel unity across our diverse cultures as we all connect with the amazing beauty of the universe. I don't have time to tell you the full story of how this came to be my mission and my work, but I can tell you that it was born from a period when I was a graduate student and my boyfriend Doug and my mother both passed away in quick succession. And I found myself reflecting, I'm still here on this beautiful planet with a beautiful life to live, and found this to be a purpose for me in my work and in my life. An influential moment for me was a few years later when I attended my first IAU GA meeting, actually, in Rio de Janeiro in Brazil. It was my first time visiting a developing country. I'd traveled a bunch before, but never to a developing country. And to have the firsthand experience of meeting people from really different backgrounds and cultures than my own. And I wanted to connect and learn from each other and share, and found that astronomy education was a beautiful way for me to be able to do that. When I finished my PhD in astrophysics, I decided to take 6 months off to do astronomy outreach in different places. I went to Guatemala, and I came here to South Africa. Kevin Govender was kind enough to host me at the OAD, which had just been formed, and that kind of formed the basis that when I started my postdoc at the Canadian Institute for Theoretical Astrophysics, I was looking for some kind of education project I could do maybe with Africa, and so when the opportunity to work with Bonaventure came, this was a perfect thing for me to do. After that, I decided to shift my career more fully towards education. So I did 2 postdocs in physics and astronomy education research. Then, when those wrapped up, I saw that if I was going to become a professor, to take the kind of traditional academic route, I wouldn't have the time to focus on the kind of projects that are most important to me. I would have to kind of do outreach on the side of my desk, and that's not what I wanted. So I took a non-traditional path, and I decided to become an independent consultant for astronomy and physics education. So I have my own business, Stribba Educational Consulting, where I do things like professional development in teaching for university educators. I do project evaluation for science education projects. I do curriculum development, advancing equity and inclusion, lots of things. So if you're interested in working with me, or if you'd just like to learn more about my journey, I would love you to visit my website or chat. And so PASEA is, of course, one of the most meaningful projects that I've been working on, and I'd love to tell you a bit about what I think makes it really unique. 3 things are our innovative curriculum, our international collaborative teaching, and our evaluation of learning effectiveness. So there is a wealth and growing body of research on teaching and learning that can help us to teach effectively and inclusively, and kind of spreading those messages and increasing them to include other parts of the world than just North America, which is where most of that research is based, is a main part of my mission. So we designed the curriculum for PASEA to incorporate results from this research. And we have a focus on inquiry-based teaching, where students learn science in ways that mirror authentic scientific research practices. We designed an activity about distances in the universe, which starts with a hands-on challenge. We hang up a model planet in a field, and we challenge students to figure out the distance to it without telling them how to do it. In small groups, they slowly discover the method of parallax. Then we have students ask questions about astronomical images that they're interested in. They choose their own question to study in a group. We help them to break that question down to focus on distance. Then they work in teams to make their own distance measurement, and then they discuss their results and they reflect on their learning. Here's a group that did it in 2019. They figured out the distance to the moon using a lunar occultation of Regulus, and you can see their pride, and we're super proud of them. One student said, "PASEA made me realize that I can think and find answers to questions on my own without external help. I can now say I can think like a scientist." We've published our inquiry-based curriculum in the peer-reviewed journal Course Source, and you can also learn more about PASEA in the journal Nature Astronomy. Next, I'd like to tell you about our international collaborative teaching. We have a very international team, as Bonaventure mentioned. 3/4 of us are from African countries, and 1/4, like me, are from outside, and half of our team are women. 5 of our members so far have returned as instructors. They're alumni who started out as students in the program and have come back to be instructors, which is awesome for them, and it's really awesome for the program. And our interactive lessons in PASEA are pair-taught by 2 instructors. So they collaborate in designing and teaching, which facilitates the exchange of teaching ideas across contexts and can help new instructors to learn new interactive ways of teaching. Third, I'd like to tell you about our evaluation of learning effectiveness. So we care to know, what do our students actually learn in the program? What do they get out of it? And one way to find that out is through surveys. So one survey that we give our students is called the Colorado Learning Attitudes About Science Survey, or the CLAS. It includes questions where students have to rate their level of agreement with statements like, "When I'm solving a physics problem, I try to decide what would be a reasonable value for the answer," or "I think about the physics I experience in everyday life." And we found that every year we've given this survey, our PASEA students' attitudes became significantly more like experts, which is a rare achievement for typical courses. We also want to know, how does PASEA impact our alumni beyond their participation in PASEA? So in 2020, we gave a survey to all of our alumni to date, which was about 200 or more. And we found that almost all of our alumni are engaged in STEM. 90% say that PASEA was very influential for their choice of career or studies. About half are studying STEM, with over 20 in graduate school and postdocs in France, Canada, South Africa, and other countries. And about 1/3 are teaching STEM. 3/4 say that PASEA influences how they teach. Their students number in the thousands and will keep growing. We've also given professional development in inquiry-based teaching to more than 20 instructors, some of whom bring back the ideas of inquiry-based teaching to their regular teaching. So what are our new and future directions? From PASEA, as Bonaventure mentioned, PASEA 2024 is to be held in Tunisia next month. Very exciting. Also recently, we held a program for alumni using robotic telescopes, which I'm going to talk about in FM10 next week on Thursday, so you can come. And then I'll also tell you briefly about a couple of projects that I'm working on leading as Stribba Educational Consulting, which builds on the work that we've done in PASEA. So with colleagues, I'm applying for funding to hold a program on innovative astronomy teaching for African university lecturers, so bringing the ideas of PASEA to the wider African astronomy community. And I'm looking to create a mentorship program for African students interested in astronomy graduate school, because so many of our PASEA alumni and beyond are really interested, but they lack the support that they need to make that step to get there. So I just want to make a final point, which others have made too, which is that astronomy education and outreach need funding. Most of the work that I've just described, and I think most ODE-related work showcased at this conference, was done by volunteers. Just imagine, there is so much more that our community could do for astronomy education in Africa and beyond if we had significant and ongoing funding. And I don't just mean for things like travel or materials, I mean for things like people's time to develop ideas, to create things, to facilitate them, to evaluate them. So we commend and are immensely grateful to the IAU for creating the ODE Prize, demonstrating the importance of education, outreach, and development to the IAU. So thank you to the IAU, thank you to Avina Vendisuk. We are so grateful. And I hope that this can boost the conversation that if we as a community believe that this type of work is important, we need to find ways to put stronger financial resources behind it, more like we have for astronomical research. And I recognize that the funding situation for research isn't perfect either, but researchers aren't expected to do their work as volunteers. So if you have ideas or opinions or connections, I'd love to talk. So just to wrap up then, thank you so much on behalf of myself and Bonaventure, thank you to the IAU, and thank you on behalf of our fellow co-directors, our instructors, our PASEA alumni, many of whom are either here or in person or online. Please connect, here's our websites, and just much love, much gratitude. Thank you.
Okay, thanks so much, Linda Bonaventure, for really putting this all together and make it also into a very sustainable program here in Africa, already having an enormous impact. And we all fully appreciate both all your work that you've put in, but also the need also for more funding to be able to continue it. Good. Comments, questions? Yeah. The microphone is coming.
Thank you. Really great talks, Bonaventure and Linda. I think in terms of sustainability, I was wondering if you have talked to ITCR and just tried to co-locate whenever the ACS schools are in Africa with PASEA, so that way, if IAU can carry some of the costs for the infrastructure, then that might reduce the need for finding completely independent money and doing completely independent logistics each time.
Well, thank you very much. You know one thing, IAU has been very supportive, and they're also a partner to what we're doing. And I'm sure if we approach them, I know they will not turn their backs on us. We have actually sometimes thought about leaving it as part of ICIA, probably modifying, maybe imagine the inquiry-based method, the method ICIA being used, that can also be a way forward. So that it could just be one school for IAU, while we match the method for PASI and ICIA together, and so we can make it move forward. We are open to any idea that can make us achieve that result and sustain the program. Thank you.
Yeah, I mean, that's an interesting point. Of course, the ICIA schools are only 1 or 2 per year, and then across the entire globe. So the number of schools in Africa is actually limited. There's clearly a need for more here in this particular region. So, and as you said, they also have slightly different goals, particularly teaching the teachers. I think that's a very important aspect of this program. Yeah. Okay. Any other comments or questions? Oh, over there. Yeah, all the way in the back. All the way in the back.
Excuse me. Thank you so much for
all of your incredibly inspiring work. So because of Canada, I'm just wondering if you know about AIMS, the African Institute of Mathematical Science, and the Perimeter Institute, the connection there, and wonder if that might be useful somehow. But it seems that you know about it.
Thank you. Yes, we do know about AIMS. I've spoken to Neil Turok. I kind of applied for a job and then it kind of didn't happen. So I don't know. I think our goals and our levels are not quite together. There hasn't been quite a match, but it is a good idea. And thank you for making the connection.
The Dunlop Institute of Astronomy and Astrophysics has been of help to us as well from Canada. So we don't, any institution that we know that can support us, we try as much as possible to reach out to them. Thank you.
Well, actually, sorry, I'll say one more thing, which is we promote AIMS to our alumni as a great next step. So our undergraduates who want to go to graduate school, it's a great stepping stone for them. And one of our alumni, Margaret Ikape, who's about to get her PhD from the University of Toronto, is an AIMS graduate, and that was a really important moment for her.
Okay, good. Well, we've had a fantastic hour here in hearing all these very inspirational talks. Oh, I see there are still 2 more talks. We have to be, well, we have only 1 more minute. So I suggest actually, yeah.
Yeah, my name is Noreli Jiwaji from Tanzania. I've known Bonaventure for many years, and I think I've been in some contact with Linda at one time. But one of the issues which I feel is essential, that both of your backgrounds are in physics. One of my biggest worry is to instill misconceptions, especially when we are teaching at a younger age. Our challenge in Tanzania is starting from the younger age. I think people are not yet really aware of astronomy as really a useful thing to understand the concepts, the fundamentals of the science. So here I feel that when we are going to do outreach or education in astronomy education, we have to be sure that we are taking people only who are really well versed in physics disciplines. So I don't know what is your opinion about anybody else, because somehow...
Let's, yeah, maybe if we can wrap up this
okay, yeah, that's my worry mainly.
You want to, yeah.
Briefly, just a second.
Just
yeah, Jiwaji, thank you for that question. It may interest you to know that any country will go to organize the PASI, we normally carry out outreach to secondary schools and primary schools to create awareness. And during advertisements, we don't limit to physics graduates. We cut across all the STEM, science, technology, engineering, mathematics students, ICT students. All of them partake in this. That's why PASI is a building stone for those who are not professional astronomers. Thank you.
It's indeed rooted in the physics, sure. And that's the very important part, yes. Good, we have had a fantastic hour, a little bit more, and thank you all for coming. Just a small reminder that the next round of prizes will be in 2027, and the call will come out in very early 2027. So start thinking of other teams or individuals to propose for this. Thank you so much, and again, a big, big, big applause for all of our winners.
Thank you. Thank you.